We're going to talk about astronomy introduction. In Chinese, it's called 天文学. Yeah. 天 means sky. 文 means literature. And 学 means study. So Wien's law. So wind, it's a Wilhelm Wien. He's a German physicist, and he got his Nobel Prize in 1911 for discovering Wien's law. So Wien's law is in particular for Blackbody. It's also called Wien's radiation law. And keep in mind, radiation it's part of the EM spectrum. So radiation term, it's also related to the light, and they all in the EM wave spectrum. So let's introduce some terminology, white body and black body. So black body, it's an ideal, it's a model. Let me use a different color here. So it's a model, right? So it's an ideal substance. It's an ideal substance that it can emit, right? So like 放射 and absorb, 吸收 all frequency of lights. Okay, so if you can absorb all frequency of light, then it does not reflect, right? So it does not reflect. EOES does not reflect, right? 反射, okay? Then it's black, right? Because you don't reflect any light, so nobody can see you. Okay, so black body gets its name because it does not reflect. Now, white body, it reflects all frequency of light. Okay, so this is true. This is true regardless of the incident angle. Okay, regardless of the incident angle. Incident angle. So it doesn't matter what angle you come in. I just absorb you. Okay, so obviously this is the model, right? This is the ideal term. And white body, it reflects all frequency of light. It doesn't matter what your angle is. Okay, what's your incident angle? 射路. So Wien's law, what is it trying to do? It's relating this temperature, and this is in the Kelvin, right? Degree K, Kelvin. So it's also called absolute temperature. So this absolute temperature, remember, in this kind of high temperature, they are behaving like an ideal gas, right? So mostly gas, like in the sun, for example, 5800 degree K. And so they are, the T is relating to the average kinetic energy, and that's equal to 3/2 Boltzmann constant times the absolute temperature. So remember, this temperature higher means the particle, right, the ideal gas, will be having more kinetic energy. So they will be moving faster. Well, it's really, right, according to physicists, it's really more of the vibration, right? So back and forth. The vibration of the gas, right, that determine what kind of lights will you emit, right? Remember, the EM wave, it's due to accelerated charges, right? EM waves is, so EM wave, as we recall, right? EM wave, you can generate, any object can generate EM wave, right? It's accelerated, 加速的, right? Accelerated charges. So 电量, right? In Chinese. So positive, negative, right? So as long as you accelerate charges, then the EM wave will come out. So like our body, we like get out this infrared, right? 红外线, right? It gets, because our body has atom. And inside our body, this atom has the charges. It has proton, obviously, it has electron. So it's doing vibration. The atom is going back and forth and left and right and front and back. So when they do that, it would get this electric field out, and then at the same time, electric field will induce the magnetic field. So then this EM wave will keep going out. So that would also happen to. So this can happen. So this, it doesn't matter you are wood or you are human body, or you are stars, suns, you are cloud, right? It all emit, right? This EM wave. Anyway, Wien's law relate this absolute temperature of a black body, right? So I mean, it doesn't work for everything, but it's close, it's approximation to the lambda at the peak, right? So let's say sun can emit all kinds of EM wave. So at the peak right there is 5800, and that's corresponding to this one. Lambda 2 here is correspond to the yellow visible light. Okay, and let me change the color here. Okay, and for human, we are at about say 33, 37, right? 37 degrees C, and that plus 273, that give you 310 degree K. And according to the calculation, right here, lambda 3, and you divide it by this 2.9 times 10 to the negative 3, this is a coefficient, right? It's the constant that Wien, right? The Wilhelm Wien discovered, right? So the lambda peak, right, of this black body, the peak referring to the highest, I'm sorry, this is the intensity, okay? So I didn't write this one correctly. This is the intensity, right? And temperature is right there, okay? So this is the intensity, right? So the highest intensity of the peak is occurring, this highest intensity is occurring at 310 degree K. And according to the Wien's law, then you can calculate what is your lambda, that the human, right? So human obviously also emit all kinds of EM wave, but at the peak, it's the infrared, right? So this is lambda 3, it's about 9350 nanometers. So it's a longer wavelength than the visible, right? So the visible, remember, visible goes from 400 to 700 nanometer, right? This is visible, okay? This is a good number to remember. So if you're larger than 750, so you are in the infrared up to a certain point, right? If you are smaller than that, then you are in the ultraviolet up to a point, right? Okay, so then for human, you will be at 9350, which is IR range. And for the sun, when it's 5800, so your temperature is higher, so then your atom is moving faster, so then it will get this higher frequency, right? So higher frequency here, it's also give you higher temperature, right? So higher temperature give you this higher frequency, which is higher energy, right? And so this one here will have higher intensity compared to the human too, and has higher power, right? So intensity is power. Remember, intensity is power divided by area, and power is equal to energy divided by time, right? And then divided by area, right? So you have a higher energy, which is like you have a higher temperature, right? When you have a higher temperature like this one here, it will have higher energy. And higher energy means higher kinetic energy here. And then that would then give you a higher, so this is the higher intensity, okay? So intensity related to power, and then that related to the energy, and energy then related to the kinetic energy, and the kinetic energy related to the temperature, all right? And the temperature here and the kinetic energy relationship is from the ideal gas. So you can kind of all relate them together, but obviously human cannot use this formula here, right? But for sun, it's basically all the gas. Okay, so looking at this is the lambda axis, which is your wavelength, 波长. This is the wavelength of your EM wave, right? So your EM radiation, 辐射, okay? 辐射 in Chinese, right? So EM radiation, it's the wavelength, and that has a relationship to the temperature, and that temperature has a relationship to the kinetic energy, and that kinetic energy has a relationship to the power, and it depends on your area, then you can calculate your intensity, and that's what WINS and the Blackbody specialists, Einstein also got involved with Blackbody, and they come up with this curve right there, which is very, very interesting. Okay, we're gonna stop there, and thank you for watching, and hopefully you will keep watching and keep learning more physics. Bye-bye now.